Ok, donc je vous propose de démarrer la session donc, sur l'optimisation des requêtes avec un premier exposé de Stamatis, Zampetakis sur le ClickSquare.
Hello, my name is Stamatis. I'm a second-year PhD student at INRIA and University Paris Sud. I also work for O-Team of INRIA. And today I'll present you ClickSquare, an efficient Hadoop-based RDF query processing framework. This work has been done in collaboration with François Goasdoué, Zoi Kaoudi, Ioana Manolescu, and Jorge Quiané-Ruiz. So the starting point of this work is the important volume of RDF data. The idea is that you can find RDF data everywhere, from biology to television and demographic statistics and everywhere. If you have been to our demo, you could also see that we use RDF even for fact-checking and fact-minding. Below you can see some RDF databases like UniProt and BioRDF, which are related to biology. And this is what we call linked open data. Each circle in this graph is an RDF database. The idea is that this data from 2007 to 2011 and now are getting bigger and bigger each year. So if we see it in numbers, we have almost 31 billion triples, and if we convert it to gigabytes or terabytes, we have almost 6 terabytes of information. With 6 terabytes of information, we cannot do much in a single isolated machine. So what we can do is move to massively parallel processing frameworks. Towards this direction, we propose ClickSquare, which is an efficient RDF query processing framework based on Hadoop. And Hadoop open source MapReduce implementation and its file system HDFS. So what we provide a novel partitioning and storage model to minimize data transfer at query time. And also provide an evaluation algorithm for maximizing query performance by exploiting local joins and minimizing the number of MapReduce jobs. We are not the first that we are deal with this problem. There are 3 main categories that we can divide the current work. So we have solutions that rely solely on Hadoop and its file system HDFS. We have solutions that rely on key value stores, on SQL key value stores. And we have other works that try to answer the query in independent RDF stores, or use cloud services and store the data in RDF Amazon Cloud and Amazon Web Services. Obviously, our work is related with the first category. And in this category, the state of the art in RDF query processing is currently Hadoop RDF. And this is how we compare our system with in the experiment section. So here you can see a brief outline of what we will see today. We will see some preliminaries about RDF and MapReduce. Then we will see how we store data on ClickSquare and how we process this data in the query time. Then we will conclude with some first experiments and discuss a bit about future work. So let's see some basic things about RDF. RDF is a W3C standard for describing web resources. RDF is comprised from triples, which are statements of the form subject, property, and object. For example, you have a statement which is student 1 takes the course database, and we can see that student 1 is a subject, takes course is a property, and the database is the object. Similarly, we can have that the student 2 takes another course, We can have a professor who is the advisor of student 1, and etc. This data can be represented as a graph, as shown on the bottom of the slide. The basic query language to get back information about RDF data is SPARQL. So SPARQL is similar to SQL. It has, for example, select clause, where clause, and its basic built-in block is triple patterns. And what is a triple pattern? Is a triple of the form SPO, subject, property, object, which can be either which can have either variables or constants. And we can see that we have a conjunction of triple patterns in the body of a SPARQL query. To see an example of how this is evaluated on a sample RDF data, so we take first the triples that match T1, triple pattern 1. Then we take the triples that match triple pattern 2. We perform the join on the common variable x, and we get the result. And then we project our result on y. Now, what is MapReduce? I suppose that all you already know, but I will go with some brief stuff. So MapReduce is a programming model, a paradigm for handling huge data with a distributed and parallel algorithm. The MapReduce is comprised from jobs, and each job has a map phase and a reduce phase. In the map phase, we divide the input into smaller inputs, and we assign them to different tasks. So each different task handles its different input. Then we do some processing on the data in the map function, and then we create some key value pairs. These key value pairs are sent to the network, and then in the reduce phase, the pairs that have the same key are grouped, and we can have the same key and a list of values. Then we have a reduce function that applies some operation on this data. Now I will show you how we store this data. We store RDF data using MapReduce and Hadoop. So each triple of our RDF data is partitioned based on its subject, property, and object. For example, we can see here that we have a sample setup with 5 nodes, 5 computers. And we start by sending the triple by its subject, by student 1. Then it ends up in node 1 because of its subject. We send again this triple by its property, and for this it ends up on node 3. And we send the triple by its object, and it ends up again on node 3 because of the object, which is the partition attribute or the hash key, differently. We will show it again for triple 2, just to make sure that we understand what we are doing. And we hash it by the subject, which is student 2, and it ends up on node 2. We hash it by property, and it ends up on node 3. And what we can note here is that triple 1 and triple 2 will be on the same node, node 3, because they were hashed with the same value of property. We hash again with the object, and we store it on node 4. And we conclude our example by storing 2 more triples. And then we have this. In the second step, what we can note here is that triples, as we said before, that share the same value, will appear in the same node. For example, triple 1 and triple 3 here share the value student 1 in the subject and the object, and they will be located in node 1. For this this is what allows us to perform a large number of joins locally at each node without sending a lot of data in the network. Actually, no data in the network. In the second step, what we do is to group the triple patterns, which are already in the nodes, into 3 partitions: the subject partition, the property partition, and the object partition. And we do this based on the partition attribute. So we can see that with blue color, we have the subject partition. With green color, we have the property partition. And with purple color, we have the object partition. After we group the triples into partitions, we create for each property in each partition a file in the Hadoop distributed file system. And we name this file by the name of the property. As, for example, here, we have one property for the property partition, and thus we will create a single file. The advantages of this storage model are the following. So, a large number of joins can be performed locally at each node. Then, neither too many nor too few files are generated in the Hadoop file system. And the redundant information is minimized for this reason. Because the property distribution of property values in RDF is not uniform, we have problems with skew. So we have very big property files. And how we deal with this issue is simple by having a threshold. And when the file gets too big, we split these files into multiple and make sure that they end up into different nodes. Now let's see how we process this data using MapReduce. So our processing algorithm relies on 2 basic notions, which is variable graphs and variable clicks. And what is a variable graph is simply by taking a SPARQL query, we can create the variable graph by making a node for each triple pattern of the query. So each triple pattern of the query corresponds to a node in the graph. Then how do we connect these nodes together? We connect these nodes together by the variable that they share in the triple patterns. So because T1 and T2 and T3 send variable x, we have edges x on between these 3 nodes. And the same for variable, and the same for variable w. Then, about the second notion, the variable click. A variable click is a set of nodes which are connected to each other with the same edge. For example, we have the click of x, which is this, because all of these nodes share the variable x. And we have another click, the click of w, for the nodes that share the same variable w. An important category of queries, we define this category of queries as one-click queries. And as denoted by their name, is just the queries that contain only one click in the graph. So we can see that all these queries, all these graphs, have only one edge, only of one type of edge, x. And this is why they are called one-click queries. And why are we interested in this specific category? Is because these queries can be answered very efficiently because of our partitioning scheme in, let's say, half a job, in the map phase of a MapReduce job. And based on queries posed in the BDA endpoint, based on the study that we conducted, we have seen that 99.1% of them are one-click queries. Another important category of queries is what we call central click queries. And let's make this a one-click query, and we make it a bit more complicated. And what is a central click? A central click query is simply queries that have a click which intersects with all the other clicks of the graph. We can see here that the red click, the click of x, intersects with all the other clicks in the graph. And that's why this query is a central query. These queries can also be answered very efficiently in a single job, in one job of MapReduce. And how we do this is by executing each one-click subpart of the query in the map phase. And then, in the reduce phase, we perform the join on the variable of the central click. And again, based on the study in Wikipedia, in queries posed in the Wikipedia endpoint, we can see that this is that 99.3% of them are central click queries. Now, let me give you the general idea of our algorithm for queries that don't fall in the first two categories. So we have an algorithm that generates plan for queries that are not one-click queries or central click queries. So the idea is that we first build a variable graph for the given query. Then we decompose it into one-click subparts. We apply some simplification. We collapse each click into a single node. Then we rebuild the graph, and we continue this procedure iteratively until we reach only one node in the graph. We will see this procedure in more detail. So we have the variable query, we have the SPARQL query, and for this, we create the variable graph as we have seen before. Then, since we are in the first level, all of these nodes of the graph will correspond to scan operators in the logical plan on the right. As we said, we decompose the graph into one-click subparts, and then we collapse each click into a single node on the new graph. And this will correspond to join operators. So we can perform the joins on blue variable, red variable, black variable, and etc. At this level, this first level of joins will be performed in the map phase of a MapReduce job. Now, using these nodes, we rebuild the graph, as we said. We create the second level of joins, which will be performed in the reduce phase of the plan. And then we continue this procedure iteratively until we reach only one node in the graph, which is the end of the plan. What we can note here is that the height of the tree determines the number of MapReduce jobs that we need to execute this query. For example, for this specific plan, we need 2 jobs. Now let's see some first experiments that we conducted in comparison with Hadoop RDF, that we said it's the state-of-the-art work on this area, on RDF query processing. And we performed our experiment in a cluster of 8 nodes, where each node has 8 quad-core Xenon processors with a total of 16 gigabytes of main memory and 600 gigabytes of hard disk. And the dataset that we used is the LUBM, which provides RDF, synthetic RDF data, and has a set of 14 default queries. This benchmark is used also from Hadoop RDF in the experiments that we run, and it's used by most of the works in this area, in RDF query processing. So in our context, all of the queries that the LUBM contains are either one-click queries, either central click queries. So from these queries, we selected to run Q1, Q2, Q4, and Q9. And while we select these queries, we will see it in the next slide. So we generate 2 datasets, LUBM 10,000 and LUBM 20,000, sorry, which is equivalently almost 400 gigabytes of data. And it has to do with universities. So the queries that we used are the following that we said before, Q1 to Q4 and Q9 from a LUBM benchmark, and Q15, which is a custom query that we created in order to have lower selectivity than the other queries that exist in the benchmark. So we want to have queries that have a various number of triple patterns, and we have selected queries with 2 to 6, with triple patterns 2 to 6. That is the maximum numbers that the LUBM benchmark contains. We selected queries with different cardinalities from high to low, and we make sure that we have one-click and central click queries. The first graph shows the experiments about how costly is the data upload to the Hadoop file system. So we have Hadoop RDF with blue, ClickSquare without skew, which is with gray, and we have the ClickSquare, which handles also skew, with green. So what we can notice here is that ClickSquare and Hadoop RDF have similar upload times, despite the fact that in our system, we store more information. We store each triple 3 times. We triplicate the data. And another thing that we should note is that without handling skew, ClickSquare couldn't partition the data for the big data set. Now, in terms of running time, of query running time, which is the most important part of this work, is that we can note that we are faster than Hadoop RDF. And in many cases, we have a big difference. For example, for this query, ClickSquare can run in 36 minutes, while Hadoop RDF runs in 176 minutes. And another thing to note is that in the time that Hadoop RDF needs to run, let's say, for example, only query 2, we can run all of the queries of our dataset, of the dataset we used. For example, we run for these 5 queries, we can run them all in time less than 176 minutes. Another thing to note is that for one-click queries, ClickSquare is not affected a lot by the selectivity of the query, in contrast with Hadoop RDF. And this happens because one-click queries don't send data in the network, and also they can be answered in the map phase of MapReduce jobs. And that's why we can note here that, sorry. And that's why we can see here that for queries 15, 4, and 1, we have only 1 to 2 minutes for executing them, while Hadoop RDF has 15 minutes for the first query and 100 for the query 4, which is the main different thing is the selectivity. Then here we can see what we are claimed in the beginning, that we minimize data transfer in the network. And we can see that in general, for all of the queries that we run, is that we send less data to the network than Hadoop RDF. Also, for specifically one-click queries, which is 1, 4, and 15, we can see that we don't send any data, we don't have any network transfer for these 3 queries. In general, from the point that we submitted the paper, we run more experiments, and we noticed also that there are cases that we perform better as a query time, but we might have a bit more data transfer for the queries that are not one-click queries. So this is an issue that we'll deal in our future work, and we already came up with some new algorithms that help us reduce this data transfer even more. Here are the statistics for the queries that I told you that were collected from the DPpedia endpoint and corresponds to real-world queries. As we said, the number of queries that we can answer in one job correspond to 99.1%, and in half job to 99.1%, and in one job to 99.3%. To sum up, what we propose in our work is a novel partitioning and storage scheme that minimizes data transfer at query time. We also have a novel evaluation algorithm that exploits local joins to maximize query performance. And in the first set of experiments, we perform better than the state of the art. As a future work, as I told you, we'll have already started working on optimization algorithms that perform even better. and reduce data transfer even more. We plan to run we plan to run more experiments in real datasets and not only synthetic ones. And finally, we plan to, let's say, in less than a year, provide a complete open source platform that can be that will be available to the public. So, thank you.
Thank you. On a le temps pour prendre 2-3 questions.
All the example of the queries that you present, it was about basic graph pattern. Basic graph pattern. Yes. Can you handle complex with optional with? For now, we have only constructive queries. Okay. Basic graph pattern. Yes. Because for optional, I think it will be difficult to apply. Or do you have any idea?
Yes. For now, we emphasize on this, and we plan to extend in the future, but we have to deal with other things first. So, because most of the queries are conjunctive. We don't, and that's why we emphasize on this query.
So in, what's the name? ClickSquare, you triplicate the data. So normally you should, when you load, you should have 3 times more IOs, but you showed that you get the same loading time. So how come?
Actually, Hadoop-RDF needs Hadoop-RDF needs 4 jobs in order to store the data, while we'll do it using only 1 job. And that's why we are faster. So, but you're doing more IOs, so how come you get the same? Because initiating a job, yes. And this is the main reason. Mm-hmm.
I have just a small question in the same direction. Do you have, or does it make sense to try to have a kind of cost model to estimate the cost of the algorithm?
Of course, we planned. Our main purpose was to minimize the number of jobs, and this is where our cost model is based. But of course, we will apply a cost model that applies also to I/O, and yes, taking into account both I/O and Hadoop MapReduce jobs. But since the overhead is big enough, it is enough to minimize the number of jobs. And this is how it's kind of handled in also the other works of in the area. So they try to minimize the number of jobs in their cost model. They have some other parameters that might take place, but the main parameter that has the biggest impact is the number of jobs.
Okay, thanks a lot. So I have a lot of questions, in fact, so we should discuss offline. But essentially, it seems that you add, there is already replication in HDFS, and there is already partitioning, native partitioning in HDFS. So they can be tuned. You can choose how you replicate and how you partition. It seems to me that you just add another layer of replication on partitioning. So if I have a 3 replication in HDFS, you will come up with 10 times the same data. So isn't it a problem, and shouldn't you focus on this kind of thing?
So this is not exactly the case. For example, our idea came up for these things, but that because Hadoop originally triplicates the data, we said that we are going to do it in a different way so that we maximize, so that we are making sure that the data are on some nodes. So we triplicate as Hadoop triplicates, but we do it yes, with a way that it's instead of using the Hadoop replication, we use our replication mechanism.
Thank you.